There is a way of seeing time that physicists have used for over a century and that almost no one outside of physics departments knows about. It is not a metaphor. It is not a pedagogical analogy to simplify something difficult. It is an exact geometric representation that captures real properties of space-time, properties that have been measured with real instruments and that have practical consequences on technologies you use every day. If you could see time that way, something would change in your understanding of what it means to be in a place, in a moment, moving in a direction. The present would cease to be a passing instant. It would become something with a shape, with geometry, with a structure that includes not only where you are, but what you can reach, what you can no longer change, and what still cannot affect you. Penrose spent decades working with that geometry, first in the context of the singularities of black holes, in the work he shared with Stephen Hawking in the 60s and 70s of the last century, later in his research on the nature of consciousness. And throughout all that work, he constantly returned to the same tool, the space-time diagram. A way of drawing on paper something that is normally impossible to visualize. 4 simultaneous dimensions, 3 of space and 1 of time, collapsed into an image that reveals the causal structure of the universe. The diagram was invented by Hermann Minkowski, the mathematician who was Einstein's teacher at the Federal Institute of Technology in Zurich. In 1908, 3 years after Einstein published Special Relativity, Minkowski delivered a lecture that began with a phrase that became one of the most cited in 20th century physics. He said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. That union is what we call space-time. And the diagram Minkowski developed to visualize it is the tool physicists have worked with ever since. The central idea is so simple, it is almost disturbing. You take a plane. On the horizontal axis, you represent space, position. On the vertical axis, you represent time. Every event, everything that happens in a specific place and moment is a point on that plane. And the motion of any object through time, its complete history, is a line on that plane. A line that goes straight up if the object is at rest, that tilts if the object is moving, but that can never tilt more than 45 degrees from the vertical because that would represent moving faster than light, and nothing can do that. That restriction of the 45 degrees is what generates the most important structure of the diagram, the light cone. There is something in the economy of that diagram that Penrose found genuinely satisfying. With just 2 elements, a spatial axis and a temporal axis, and with the 45-degree restriction encoding the speed limit of light, the diagram captures the entire causal structure of the universe. There is no need to describe forces or fields or interactions. Geometry alone determines what can affect what can influence what is forever beyond the causal reach of any given event. That geometric austerity is not a simplification. It is a revelation. It says that the deepest structure of physical reality is not that of objects pushing and pulling each other with forces acting at a distance. It is that of a 4-dimensional geometry with a causal structure encoded in the 45-degree angles of the light cone. Forces are secondary, geometry is primary, and time is part of that geometry, not an external stage on which geometry occurs. It was looking for answers to this that I found this digital book, The Penrose Dossier. What academia fears to admit is not a geometry manual or a summary of relativity. It is something harder to describe and more valuable. It is a training in the mental posture that makes it possible to hold an image that completely contradicts your intuition until that image becomes clearer than the intuition it replaced. Penrose built his understanding of space-time using diagrams, not as illustrations of ideas he already had, as instruments of thought that allowed him to see things that would otherwise have been invisible. This book documents exactly that disposition, using geometry as a lens, not as a decoration. You are at the precise moment when a new image begins to form, and the old one has not quite given way. That is exactly the moment when it is worth acting, not waiting for the discomfort to pass. The link is in the first pinned comment, but beware, this content may be taken down. Click now. Download your copy. Have you ever thought of time as something with a shape, as something that has a geometric structure? What would change in how you live if you saw it that way? Leave your answer in the comments. The light cone is the figure that appears when you draw on the space-time diagram all the possible paths that light can take from a given event. Imagine that in this moment, in this place, you turn on a flashlight in all directions simultaneously. The light expands outward in all directions of space. On the diagram, that expansion traces a cone that opens upward into the future. But there is also a cone that opens downward into the past. All the trajectories of light that could have reached this event from any direction. The present event is trapped between those two cones, and here is the structure that changes everything. The inside of the future cone contains all the events that this moment can causally influence. They are the only places and times in the universe you can reach, the only ones you can affect, because to get to them you need to move at a speed less than that of light, which is within what is physically possible. Everything outside the future cone is causally inaccessible from here. No matter how hard you try, you cannot send any signal, any influence, any effect to any event outside that cone. The speed of light is not just a speed limit. It is the limit of causality. The inside of the past cone contains all the events that could have causally influenced this moment. They are the only events in the universe that could be, in some sense, responsible for what is happening here and now. Everything outside the past cone is causally inaccessible from the other side. It could not have affected you, no matter what happened there. And the region that remains outside both cones, the space physicists call the space-like region, is something even more disturbing. That region is neither the past nor the future of this event. It is something for which ordinary language has no name, because human experience has never needed it. They are events that are simultaneous with this moment for some observers and are not for others. Events that are too far away for light to have been able to travel between them and this point in either direction. Events with which there is no possibility of causal connection in any sense. When you see that structure drawn on a diagram, when you see the light cone with its two halves and the space-like region surrounding it, something changes in your understanding of the present. The present is not a horizontal line that crosses the diagram. There is no such line that is universal. The present, in the geometry of space-time, is the vertex of the cone, a point, not an extension. And what we call the extended present, the whole world in this moment, is a construction that our perception makes, not a physical entity that exists independently of us. Penrose used to teach this with a specific question that always baffled his first-year students. He would ask, "What is happening right now in the center of the Andromeda Galaxy?" The intuitive answer is that there is something happening there now, but Andromeda is about 2.5 million light-years away. The light we see from it left 2.5 million years ago. And given that simultaneity is relative to the state of motion of the observer, the question of what happens there in this instant has no single objective answer. For an observer at rest relative to Earth, the present in Andromeda could be a particular instant of its history. For an observer walking in the opposite direction, the present in Andromeda could differ by thousands of years. Both are equally correct. There is no universal now stretching across the galaxy. There is a property of the light cone that deserves particular attention because it transforms the way we understand simultaneity. When we look at a star in the night sky, we do not see it as it is now. We see it as it was when the light reaching our eyes left it. For a star 10 light years away, we are seeing its past from 10 years ago. For Andromeda, we are seeing what happened 2.5 million years ago. On the space-time diagram, this is perfectly visible. We are at our vertex of the light cone, and the information we receive comes from inside our past cone, not from a shared present with those sources. What this means is that astronomical observation is always temporal archaeology. The telescope is not a window to the universe as it is now. It is a time machine that allows us to see regions of the past at different depths, depending on the distance. And the farthest objects we observe, the galaxies billions of light years away, are regions of the past cone so remote that the universe was fundamentally different when that light left. The image of the night sky is not a portrait of the universe in this instant. It is a temporal stratigraphy, a set of layers of the past at different depths. The link is in the first pinned comment. The last units are running out. Click now and start your journey towards the clarity and genius you deserve. But the space-time diagram does not only reveal the causal structure of the universe. It reveals something about time itself that is even more baffling. That time does not pass at the same speed for all objects. This is not philosophy or interpretation. It is a fact measured with real instruments, with precision down to nanoseconds. In 1971, physicists Joseph Hafele and Richard Keating placed cesium atomic clocks on commercial airplanes that flew around the world eastward and westward, and compared those clocks with identical clocks that remained on the ground at the United States Naval Observatory. When the airplanes landed and the clocks were compared, the results matched the predictions of combined general and special relativity. The clocks that had flown showed different times from those that had remained on the ground, not because of instrument failure, because of real-time dilation. Time passed at slightly different rates for objects in motion and in different gravitational positions. The global positioning system, the GPS you use when you navigate by car or on foot, depends on correcting this effect in real time. GPS satellites orbit at an altitude of about 20,000 kilometers and move at approximately 14,000 kilometers per hour. At that speed and at that distance from the Earth's gravitational center, satellite clocks experience two opposing effects. They slow down because of the speed, according to special relativity, and they speed up because they are in a weaker gravitational field, according to general relativity. The net effect is that the satellite clocks run fast by about 38 microseconds per day relative to clocks on the Earth's surface. If that accumulated error were not corrected, navigation systems would accumulate a positional error of several kilometers per day. GPS works because engineers applied the relativistic corrections precisely. The curvature of space-time by mass has an effect on time that is especially counterintuitive when formulated precisely. Clocks closer to a massive mass run slower than clocks further from it. On the surface of the Earth, time passes slightly slower than at higher altitudes. The difference is minuscule on human scales, on the order of microseconds per year for altitude differences of a few kilometers. But it is real, measurable, and has practical consequences in high-precision engineering systems. If you lived on the surface of a neutron star, An object with a mass comparable to the sun compressed into a radius of just 10 kilometers, time would pass for you noticeably slower than for someone far away from that gravitational field. Gravity does not just curve space, it dilates time. And at the extreme limit, at the singularity of a black hole, the curvature of space-time becomes so extreme that time, from the perspective of an outside observer, appears to stop completely at the event horizon. The geometry of space-time is not uniform. It has regions where time is dense and regions where it is lighter, and that variable density of time is what we call gravity. This means that every time you use your phone's navigation, you are using a system that was designed with Einstein's general relativity as its engineering foundation. Time is not uniform. It is a property of space-time that varies with speed and gravitational position, and that variation is not an abstract effect that only matters in extreme situations. It is a real effect that engineers had to correct for the satellites to function properly. Penrose took this point further than engineering techs usually do. He wasn't just interested in the fact that time dilates. He was interested in what that means about the nature of time. If time passes more slowly for a fast-moving object or more slowly for an object near a gravitational mass, then time is not a uniform background against which events occur. Time is part of the geometry. It is one of the dimensions of a structure that curves and stretches according to the distribution of mass and energy in the universe. This is the image that general relativity adds to the Minkowski diagram. The flat diagram of special relativity assumes that space-time is flat, like a sheet of paper. General relativity shows that space-time curves in the presence of mass. Earth curves space-time around it. The sun curves it more. A black hole curves it to the extreme. And that curvature is not just a visual metaphor. It is a real geometric structure that determines how objects move and how time passes in each region of space. Gravity, in Einstein's physics, is not a force acting at a distance between massive objects. It is the curvature of space-time caused by mass. When Earth orbits the sun, it is not being pulled by a force. It is following the straightest possible path in a space-time curved by the mass of the sun. What in the flat diagram would be a straight line, in the space-time curved by gravity is a trajectory that circles the sun. The geometry of space-time makes the orbit the natural path, without the need to invoke any mysterious force acting at a distance. The link is in the first pinned comment. The last units are running out. Click now and start your journey towards the clarity and genius you deserve. There is a consequence of the curvature of space-time that Penrose considers especially significant, and that connects general relativity with the question of what time is in a way that few popular texts explore with sufficient depth. That consequence has to do with the concept of proper time. Proper time is the time measured by a clock, traveling with a specific object along its world line, not the coordinate time that we conventionally assign to events from an external frame of reference. An object's proper time is the duration that object experiences along its own trajectory in space-time. And there is something remarkable about how that proper time is calculated. It depends on the geometry of the trajectory. Two objects starting from the same event and arriving at the same final event may have experienced different proper times if they took different paths in space-time. The most famous version of this is called the twin paradox. One of two twins sets off in a spaceship, accelerates to near the speed of light, travels for what seems to him a few years, and returns. The other twin remains on Earth. When they reunite, the traveling twin has aged less than the one who stayed. Not metaphorically. In a literal sense, his body experienced less time. His cells divided fewer times, his clocks tick fewer hours. This is not a paradox in any technical sense. It is the geometry of space-time acting on physical objects in ways that completely contradict the Newtonian intuition of a universal time flowing equally for everyone. Penrose points out that what makes the twin paradox especially instructive is not the result, which is experimentally verifiable with high-energy particles and the atomic clock experiments already mentioned. What makes it instructive is what it implies about the nature of proper time. That proper time is not a property of the universe. It is a property of the trajectory. Every object has its own time, determined by the geometric path it has traveled in space-time. There is no universal background time. Time is local, relational, geometric. And this is where I need to speak to you directly, because there is something in this picture that has immediate consequences on how you inhabit the present. If time is a geometric dimension, if the present is not a universal horizontal line but the vertex of a light cone specific to your position and state of motion, if the time you experience is the proper time of your trajectory and not the coordinate time of any external clock, then the question of what the present is acquires a specificity that makes it more real, not more abstract. Your present is not an arbitrary convention. It is the product of your specific history in space-time, the path your body has traveled, your mass, your relative speed, your position in Earth's gravitational field. All of that determines the time you have experienced, the nanoseconds that have passed for you and not for others. That means that the time you have lived is literally yours in a precise geometric sense. It is not the time others have lived. It is the proper time of your specific world line, determined by every kilometer you have moved, every meter of altitude you have gained or lost, every second you have traveled at a greater or lesser speed. Your life is, in the most technical sense in physics, a unique trajectory in space-time, and the time you have experienced along that trajectory is a geometric magnitude that belongs only to that trajectory. Penrose did not draw any sentimental conclusions from this, but he did point out that the image of time as a geometric object, as a dimension with structure and curvature, fundamentally changes the question of what it means to live in time. Living in time is not being swept along by a current that flows in one direction. It is traversing a trajectory in a four-dimensional geometry, choosing, within the limits imposed by physics, which path to take. And the different possible paths correspond to different proper times, different amounts of experience duration, different configurations of the light cone that delimits your causal access to the universe. There is something that should be clarified at this point, because it is easy to take this image too far in a direction that physics does not justify. The fact that time is a geometric dimension does not mean that you can move through it at will as you move through space. The geometry of space-time has an asymmetric structure. You can move in any spatial direction, but in the temporal dimension, you can only move in one direction, toward the future of your light cone. The reason for that asymmetry is not in relativity itself, which, as we saw, is symmetric with respect to the direction of time in its fundamental equations. The reason is in the second law of thermodynamics, in the increase of entropy that distinguishes the past from the future in a way that the geometry of space-time alone does not distinguish. Penrose has worked on this problem with a depth that few other physicists have reached. His proposal, which he calls conformal cyclic cosmology, argues that the temporal asymmetry of the universe has its origin in conditions of extraordinarily low entropy at the Big Bang, that the universe began in a state of geometric order so improbable that its subsequent expansion towards states of higher entropy, which is what we call the arrow of time, was an inevitable consequence of that initial state. And that understanding the arrow of time requires understanding the geometry of the Big Bang, not just the statistical mechanics of gas molecules. This is the point where relativity, thermodynamics, and the geometry of space-time meet in a way that still does not have a complete answer. And Penrose, who has spent decades working at that intersection, is perhaps the living physicist who has thought most deeply about it without claiming to have solved it. So keep this image. There is a diagram that physicists draw to represent space-time. In that diagram, every event is a point. Every object is a line. Every line is wrapped in a light cone that delimits its causal past and its causal future. And time, in that diagram, does not flow from left to right or from top to bottom. Time is the vertical axis, a geometric dimension like the others, with the difference that you can only travel along it in one direction. When Minkowski said that space by itself and time by itself were doomed to disappear, he was not reducing time to something less than what it seems. He was elevating both time and space to something more than what ordinary intuition attributes to them. He was making them parts of a unified geometric structure that is more real, more lasting, and richer than any of its components separately. Time does not flow. It exists. And its existence, with all its light cones and its proper times, and its gravitational curvature, and its thermodynamic asymmetry, is one of the most complex, most beautiful, and most difficult objects to understand that physics has discovered, not as an academic curiosity, as the structure in which everything that has happened, everything that is happening now, and everything that will happen occurs, including this conversation, including the instant when this becomes clear to you.